Welcome! In this lesson, we'll study carboxylic acids and their derivatives. You'll learn about their structures, properties, reactions, preparation methods, and how different derivatives are formed. This is an important topic because it links together many organic chemistry concepts and often appears in A-level exam questions. Course context and A-level specification requirements, the carboxyl functional group and general formula, IPAC nomenclature of carboxylic acids. Carboxylic acids are a core part of organic chemistry which includes functional groups, intermolecular forces, acidity, and nucleophilic substitution. Students are required to understand the structure and bonding of the carboxyl group, COOH, explain physical properties such as boiling point and solubility, and describe the characteristic reactions of carboxylic acids. These include reactions with metals, metal oxides, metal hydroxides, and carbonates, which demonstrate their acidic behavior. In addition, students must understand how carboxylic acids are prepared, particularly by the oxidation of primary alcohols and aldehydes using oxidizing agents such as acidified potassium dichromate, 6. Carboxylic acids are defined by the presence of the carboxyl functional group, written as COOH. This group consists of a carbonyl group, C equals O, bonded to a hydroxyl group, OH, attached to the same carbon atom. The general formula for saturated monocarboxylic acids is CHCOOH, where the alkyl chain can vary in length and structure. Examples include methanoic acid, HCOOH, ethanoic acid, CHCOOH, and propanoic acid, CHCHCOOH. The presence of both a polar C equals O bond and an OH bond gives carboxylic acids distinctive chemical and physical properties. The carbonyl group is strongly polar due to the electronegativity difference between carbon and oxygen, while the OH bond allows hydrogen bonding. The name of a carboxylic acid is based on the longest carbon chain that includes the carboxyl carbon, which is always assigned carbon number 1. The suffix oic acid is used in place of the alkane E. For example, a 2-carbon carboxylic acid is named ethanoic acid, while a 3-carbon acid is propanoic acid. When additional substituents are present, their positions are numbered relative to the carboxyl carbon. For instance, 2-methyl-propanoic acid contains a methyl group attached to carbon 2. Unsaturated carboxylic acids are named using the enoic acid suffix, such as but 2-enoic acid, where the position of the C equals C double bond must be specified. Boiling points and intermolecular forces, solubility trends in water, acidity of carboxylic acids, and resonance stabilization. Carboxylic acids have relatively high boiling points compared with alkanes and even alcohols of similar molar mass. This is primarily due to strong intermolecular hydrogen bonding. Each carboxylic acid molecule can form 2 hydrogen bonds with another molecule, resulting in the formation of hydrogen-bonded dimers. These dimers significantly increase the amount of energy required to separate molecules during boiling. For example, ethanoic acid has a much higher boiling point than ethanol, despite having a similar relative molecular mass. The solubility of carboxylic acids in water depends on the balance between the hydrophilic carboxyl group and the hydrophobic hydrocarbon chain. Short-chain carboxylic acids, such as methanoic and ethanoic acid, are completely miscible with water because the COOH group can form strong hydrogen bonds with water molecules. As the carbon chain length increases, the non-polar hydrocarbon portion becomes more significant, reducing overall solubility. For example, hexanoic acid is only slightly soluble in water. Carboxylic acids are weak acids, meaning they partially dissociate in aqueous solution to release H ions. Their acidity can be explained by the stability of the carboxylate ion formed when the acid donates a proton. The negative charge on the carboxylate ion is delocalized over 2 oxygen atoms through resonance, making the ion more stable. This stabilization explains why carboxylic acids are stronger acids than alcohols, where the negative charge on the alkoxide ion is localized on a single oxygen atom. Preparation by oxidation of primary alcohols and aldehydes, reactions with metals, bases, and carbonates. Carboxylic acids are commonly prepared by the oxidation of primary alcohols or aldehydes. The oxidizing agent typically used is acidified potassium dichromate, 6, KCrOH. When a primary alcohol is heated under reflux with excess oxidizing agent, it is fully oxidized first to an aldehyde and then to a carboxylic acid. For example, ethanol is oxidized to ethanoic acid. Reflux is essential to prevent the volatile aldehyde intermediate from escaping before further oxidation occurs. Alternatively, aldehydes can be directly oxidized to carboxylic acids under similar conditions. Carboxylic acids show typical acidic behavior in their reactions with metals, metal oxides, metal hydroxides, and metal carbonates. When reacting with a reactive metal such as magnesium, a carboxylic acid forms a salt and hydrogen gas. For example, ethanoic acid reacts with magnesium to produce magnesium ethanoate and hydrogen. With metal hydroxides or oxides, neutralization occurs, forming a salt and water. Reactions with carbonates or hydrogen carbonates produce a salt, water, and carbon dioxide, which can be identified using lime water. Esters, formation and properties, acyl chlorides and their high reactivity, acid anhydrides and amides. Esters are carboxylic acid derivatives formed when a carboxylic acid reacts with an alcohol in the presence of a concentrated acid catalyst, typically concentrated sulfuric acid. This reaction is known as esterification and is reversible. For example, ethanoic acid reacts with ethanol to form ethyl ethanoate and water. Esters often have distinctive sweet or fruity smells and are used in food flavorings and perfumes. Acyl chlorides are among the most reactive carboxylic acid derivatives due to the presence of the highly polar C-Cl bond. They readily undergo nucleophilic addition elimination reactions with water, alcohols, ammonia, and amines. For example, ethanol chloride reacts violently with water to form ethanoic acid and hydrogen chloride gas, producing steamy fumes. This high reactivity means reactions usually occur at room temperature without the need for catalysts. Acid anhydrides are less reactive than acyl chlorides but more reactive than esters. They react with water to form two molecules of carboxylic acid and with alcohols to form esters. Amides are formed when acyl chlorides or acid anhydrides react with ammonia or amines. Amides are relatively unreactive due to resonance stabilization involving the nitrogen lone pair. Relative reactivity and reaction pathways, required practicals, data interpretation, and exam technique. The relative reactivity of carboxylic acid derivatives follows the general order: acyl chlorides, acid anhydrides, esters, amides. This trend is explained by the ease with which the leaving group is displaced during nucleophilic addition elimination. Chloride ions are weak bases and excellent leaving groups, while amide ions are strong bases and poor leaving groups. To summarize, carboxylic acids contain the COOH group and behave as weak acids. Their derivatives, including acyl chlorides and acid anhydrides, are much more reactive and undergo nucleophilic addition-elimination reactions. Understanding these reaction pathways and comparing their reactivity will help you answer many A-level chemistry questions with confidence. Thank you for watching.